So hi everyone, in this video presentation I'm going to talk about the power spectrum. When we say power spectrum, it will most likely answer the question how much power are there in a signal per unit of frequency. And by that, we have formulated exercises which will prove that it is true. So given a scenario, we have to sample 10,000 points over an interval of 3.4 seconds. The signal will be a 10 Hz sine wave. We will compute the power and plot it versus frequency in Hz. In number 1, we are to create a function that will take a dataset, and the input argument should be the frequency in Hz, number of points, and the actual time spanned by the data. And it should return two vectors, the frequency and the power. We have to include some melogy to plot and use axis 0 f times 2 where f is the frequency in Hertz, just to zoom and observe in what frequency have the strong peak. So I have already following. This is the frequency in Hertz, this is the time of interval and the number of points. And I have already created a function. This is to define time as commented. We have to define it in seconds. This will be the function, and this will take the absolute value of the fast Fourier transform of this signal, and this one is to just take the positive half of this one since it will give you a symmetrical value. And obviously this one is the corresponding frequency. And there we go, you have the semilogy and the axis. This semilogy is used to show the logarithmic graph of your function. So now we're going to do it, and as expected we have to get a very strong peak at the frequency of 10 Hz. Okay, so in 1.1 we are going to use the function we created and use the following data except for the time of interval. We are going to vary it from 5, 10, and 20. Now let's do it. 5, there it is. 10, there it is. And when time interval is 20, there we go. And in 1.2 we are asked to observe on what is happening with the signal. I have saved the following. I'll take 5 and 20 as my sample for a better observation, much clearer graph. Here we notice as we increase the time of interval, the gap between the signal becomes closer, and the peak, wherein the strong peak at frequency, it becomes steeper. So that would be for our observation. Now moving on to number 2, we are to record and then play back 5 seconds of data sampled at 44,100 by using record function and the sound function. So we are to record, let y equals to record since 5 seconds. This is the frequency we're going to use. 1, 2, 3, 4, 5. Exactly 5. And we are to play it for 100. There you go. And it was stating to plot the acquired data, we'll just simply plot the data y, and there you go. See five strong frequencies. And in number 3 we are with this statement. See to it that we are asked to find the minimum number of uniform quantization levels and the minimum number of bits per sample needed. And in letter B, we are to calculate the system bandwidth required for the detection of such a PCM signal. I'm going to use this for my solution. We know that the SNR peak due to quantization error is 3L squared. And we also know that SNR dB is equal to 10 log of the SNR. So what we must do is to plug this in here, and by that we would have, and we need an output of 30 dB. So by this we should be able to get L, which will be 18.26, and we need an integer, so let's make it 19 levels. Now that we know the number of levels, we can use it to find the number of bits per sample. We know that the number of levels is equal to the 2 raised to n, where n is the number of bits per sample. So we can use the logarithmic function log base 2, and now we know L, which is 19. We would get something like this, 4 point something, but we need 5. We need an integer rather, so let's make it 5 bits per sample. Now we have the following data, and given the sampling frequency of 6,000 samples per second, and we know that there are 5 bits each sample, therefore we get 6,000 times 5 samples per second. We need to find the time duration of the bit by simply this equation, and we would get 33.3 microseconds. Now we know the time duration of the bit, we would be able to get the bandwidth of the system, which is just this reciprocal, and we would get 30.03 kilohertz. That's it. Okay. And in number 4, given the sampling frequency 650, okay, we are asked to generate spectral signal with an angular frequency of cosine 2 pi 100t. We'll be needing this one, and I've prepared a code for that one, I think. Okay, this is the one that I've prepared. This is the sampling frequency, this is the sample time, the length, time vector in steps of 1 millisecond, and this would be the signal. And of course we're about to get the fast Fourier transform of the signal. This one is to estimate the power spectrum of the given signal, and of course the corresponding frequency. So now we're going to copy and paste it on the command window, and we should plot There you go. As you will notice, at frequency of 100, there is the very strong peak. Okay. So moving on, an analog signal duty multiplied by the radius. We are asked to find the spectrum signal C3 and assume that T is equal to 0, corresponds to the midpoint. My solution for that is this one. Assuming that T is equal to 0, the fast Fourier the Fourier transform expansion of C of t would be this one, where f of s is the sampling frequency, and we are to multiply this C of t with G of t. That will result to this one. We'll just add G of t, and by getting the Fourier transform of this of the both sides, we will get this equation. And we notice that this will just be the replica of the original signal. So that's it. And for the last one, number 6, we are given the following inputs, and some of them are periodic, which mean they repeat through time. This A, B, and C are the ones were periodic signals. This one, of course, is just a pulse. And we are about to create a function that will accept data and return two vectors. So I have created one. Basically, this was just similar to the first one. The input arguments have varied only such that I'm taking the sampling frequency in the input function. So first, we are to get, and second rather, we are to get the input wave and the corresponding output by using plot function. First one is the sine wave. I've prepared it already. Sine wave. So this is wrong. I've not set the following parameters. There it is. There, I'm going to copy the sine wave. Got it. So applying the function, give us something like this. It's the power spectrum of a sine wave. And for a cosine wave, we would get something like this. It will start from 90 degrees. And plot. It's just the mirror image of the sine wave. And for the square, we got a hint there to load the signal. PKG stands for package, for us to use the square. Okay, we plot the input signal first. There's the square, and be able to use the function and plot. There's the power spectrum of the square. And lastly, for the rectangular pulse with width equals to 2, we need to set the following. So here I have prepared it already. rect pulse for the rectangular pulse. Oh, I'm almost forgot. Comma. There you go. And we should plot first the input signal. There you go. And of course I'm wrong with that because there's a pulse. So we must, oh there's a pulse. You have to show the this isn't, and we have to plot again the power spectrum of the pulse, and this is it. So this is a wrap. I've shown some techniques, functions, some computations regarding the power spectrum of periodic signals and some signals. So thank you. I'm Arden Brual and my partner is Vane Bernal. This is our project.